When you train networks like this, when you train lots of layers of features, people often ask, well, how many layers of features do you use and how many features per layer? And there's no simple answer. It's like saying, when I write a program, how many lines of code should I use? Yoshio Benjo's group did extensive experiments, and I'll describe some of them later, and he'll probably describe some of them in his talk, showing that more than one layer is a good idea. The general experience is that if you use several layers, an extra layer or one layer less doesn't make much difference. There are some problems where half a dozen layers really helps a lot more than 2 layers, and speech seems to be one such problem. And you have lots of freedom about how big to make the layers. The main point about this is the whole thing's pretty robust. You get fairly minor changes in the performance as you change the number of units per layer or the number of layers, as long as you've got several layers. And I mentioned this before, but I'll say it in print. Once you change the weights in higher layers, the inference procedure for the first hidden layer isn't correct anymore, because you've changed the prior that's coming down from above, so it no longer exactly cancels the correlations in the likelihood term. So the true posterior is no longer exactly factorial. But what we're going to do is carry on treating it as though it were factorial and rely on the fact that the changes in the weights in the layers above gained us more than we lost by having to use a slightly incorrect inference procedure. And in terms of the bound, that's true. I'm not going to go into the math of that, but it's all in this paper. Now, the first lecture, which this is the very last bit, is all about learning generative models. And you can fine-tune after you've learned, and you can fine-tune the model generatively. You don't have to fine-tune it using backpropagation. So the wake-sleep algorithm I told you about before, that assumes things are factorial, is a pretty good algorithm in these nets, because after you've done the initial learning this way, things are pretty much factorial. So the assumptions being made by the wake-sleep algorithm, that the posterior is factorial, are pretty much correct, except for the very top layer. And so you can use a version of the wake-sleep algorithm for doing generative fine-tuning. And so in the early version of this work, what I did was generative fine-tuning, where you do a stochastic bottom-up pass, and then you adjust the top-down weights to be good at reconstructing the activities in the layer below. That's the correct learning algorithm for the wake phase of the wake-sleep algorithm. And then for the sleep phase, instead of generating from your prior, what you do is you do a bottom-up pass, do a few iterations of the restricted Boltzmann machine at the top, and then generate from that. So I'll call that a contrastive version of wake-sleep. You're not going all the way to the equilibrium distribution and generating from that. You're taking the distribution you get from data, you're going a little bit towards equilibrium from that, and then you're generating. And that works very nicely for the sleep phase. And if you do that, the model gets considerably better. That is, it gets better at generating data. I'm not going to show you the demo because there isn't time, but I am going to show you a demo of something else that's related. So here's a model I trained that has 500 hidden units, 500 hidden units. So you first train these to model that. Then you train these to model that. Then we're going to train 2,000 hidden units as the latent variables to model the concatenation of 500 feature detectors and 10 labels, where this is a kind of one-hot representation where you have one of the 10 labels is present each time. So now we're giving it labeled data, but we're training a joint density model here. We're not training it to produce this given that. We're training it to model the joint density of labels and feature detectors. And we train all that with contrastive wake-sleep. And then after we've trained it, we can do interesting things with it. We can generate data, and I've got a demo on the web of doing that. But we can also do things like denoising images with it. And the most difficult form of denoising is when you have highly structured noise that's like the thing you want to see in the image. So here's some images that were generated in the following way. You take 1/3 of the pixels of a 3, and you take 2/3 of the pixels of a 4. Or alternatively, you take 2/3 of the pixels of a 3 and 1/3 of the pixels of a 4. You then just add together the pixels using 1 + 1 = 1. And so that's what you get. And you've got this model that's trained to model the joint density of digit images. And now what you do is you feed it, this is the data, and you keep the data there. So it's being fed the data all the time. But in the internal layers, you initially make it pure bottom-up, so it's doing pure inference. And then you gradually start using less bottom-up and more top-down. But you keep the sum of the bottom-up and the top-down constant. So if we go back, for this layer here, for example, initially you have 1 times these weights and 0 times those weights. But after you've done a few passes, a few bottom-up passes, you use 0.1 times these weights and 0.9 times those weights, and then 0.2 times these and 0.8 times those. And you gradually go until you're sort of half and half. So you're using top-down to clean up these first layer feature detectors. And then you look to see what you would regenerate from these feature detectors. So initially, you'd regenerate something very like the raw data. But as you add more and more top-down, you don't tell it the label here. It figures out the label for itself. But as you add more and more top-down, you expect it to clean up the image. And it does a remarkably good job of that. So if you look here, that was the initial data. Initially, from its hidden units, it would reconstruct that, which looks more like a 9 than anything else. But if you keep doing forward passes and gradually adding more and more top-down, it eventually reconstructs this. And you'll see what it's done is it's decided it's a 4, and it's reconstructed something very similar to that 4 and got rid of all the noise that comes from the 3. If you take the same example here, but with 2/3 of the 3 and 1/3 of the 4, so we've got structured noise for a 4 imposed on this 3 now, you'll see it cleans it up like that. So it does a very good job of getting rid of structured noise. I mean, this is a nice one where it pretty much completely gets rid of this 4 here, which has a lot of pixels in it, and gets something very similar to the original 3. Sometimes, of course, it can't do it. Like when you look at that, it's probably not very clear to you what that is. That doesn't, I mean, you can see that as a 3 plus a 4, but that's not what it initially looks like. And it ends up thinking it's an 8, which isn't so bad for that. There's just a few more examples of it. Here it's mixing 4s and 8s and cleaning them up as either 4s or 8s. And again, it does a pretty good job. That's just a little prelude to the idea that once you've trained these generative models, even though they're trained as top-down generative models doing bottom-up inference, you can actually start blending the two to clean up images. And you will see that much more towards the end of the summer school in Russ Salakudinov's tutorials, which will be about Boltzmann machines that are doing just that. Okay, I'm now going to talk about, once you've trained layers of features, how you fine-tune it with backpropagation. And that's the main reason why people are interested in this stuff. In fact, this is the main reason why this summer school is going on, because if you pre-train these features and then fine-tune with backpropagation, finally backpropagation works nicely. So we start off learning one layer features at a time. We then learn lots of layers. We can fine-tune it just generatively using contrastive wake sleep, or we can fine-tune it discriminatively to be better at discrimination, and that overcomes a lot of the limits of backpropagation. And most people in machine learning still think machine learning is all about discrimination. And so 20 years ago, if you looked at a textbook on machine learning, they would define machine learning as mapping from inputs to concepts. In other words, the definition of machine learning didn't allow for unsupervised learning. And then they're saying, oh, there's also clustering. And the idea of unsupervised learning was just clustering, which is a very, very primitive and dumb form of unsupervised learning. It's a mixture model. So I think learning has moved more towards unsupervised learning. It's going to keep going in that direction. I think almost all the interesting problems are in unsupervised learning. But to convince people you've done something interesting, you have to show that it affects supervised learning, because that's what the only thing the referees understand. Okay. We can learn really big networks like this. We start the backpropagation when we've already made all the decisions about what the feature detectors should be. And so it's just got to do a local search, and that's what it's good at. It's good at changing things slightly to make things work better. If you train unsupervised, you don't need much labeled data. You can get away with much less labeled data than you need if you train supervised, because the information in the feature detectors is not coming from the labels. The labels are just used to set the decision boundaries. That's probably its main advantage. The case in which it's been most impressive so far is speech recognition. And curiously, for speech recognition, they have a lot of labeled data because they worked on it for so long, they've collected these huge labeled sets. So you don't get the main win of this unsupervised pre-training in speech recognition. And in speech recognition, these nets are doing extremely well now. They will be in all the new speech recognizers, but they're not gaining much from the unsupervised learning. So here's the first example I did of training a bunch of feature detectors, even more feature detectors, with no information at all about the labels. And then you add some output units at the top, a softmax over classes, and that is multinomial logistic regression over classes, and it works very nicely. So very carefully trained backprop in the old days, before we realized you ought to make the unit stochastic, got 1.6% errors. Support vector machines got 1.4% errors, and that was one of the reasons why support vector machines replaced backpropagation, because they worked better. If you do this unsupervised learning and learn a generative model of the joint density of images and labels, and then discriminate by asking which label gives highest density when you combine it with this data, you get down to 1.25% error, although we've got that a bit lower now. If you do fine-tuning, we were initially getting about 1.15% error, although we're now down below 1% error. But that's the figure we gave in this paper. So that's a big improvement, and most importantly, this is better than that. And so unsupervised pre-training followed by generative fine-tuning works better than support vector machines for the very task on which support vector machines were first shown to be much better than backprop. Unsupervised pre-training also helps. Okay, so all of these numbers, these aren't very good numbers for MNIST, and the reason they're not very good numbers is because they're the permutation invariant version of MNIST. That is, you don't tell the network anything about the pixel structure, and you don't give it extra transformations of the images. You don't smuggle in extra knowledge by putting in transformations of the training data. You just treat it as a pure machine learning problem where it gets an input vector that's 784 numbers, and it has to say what the class is. As soon as you give it extra information by putting in weight constraints, you can do much better. If you give it extra information by transforming the training data, you can do much, much better. But even there, you can improve it still further. So for example, if you use convolutional nets with transformed data, you get numbers like this. If you now use unsupervised pre-training, you get numbers like this, which at the time was a record. The record is now down around 0.25, which is equivalent to 25 errors in 10,000 training test cases. That's done on GPUs with huge nets, trained with lots and lots of transformed data. So the current record on MNIST came from mainly the idea that you should put all your work, well, you should get a GPU to do lots of work in fitting the net, but you should put all your work into figuring out how you're going to transform the training data to give the big network more data. So the papers by Sirisan and Schmidhuber et al., they don't emphasize the point that the main point of the paper is put all your work into getting better data, and then let a GPU take care of the optimization. And use a great big net, because you've now got so much data, you can afford a great big net. If you're not going to do that, so you have a limited amount of data, it still helps to use pre-training. So the most impressive example to date, I think, of deep learning, or certainly one of the most impressive examples, it started in 2009 with a couple of students in my lab who, while I was away on holiday, decided to try this on speech. And they tried a very deep net, actually deep, that was as many as I could bear to draw, but they actually did a net with 7 layers. and a lot of parameters. So these are totally connected. So there's 4 million parameters there, and 4 million there, and 4 million there. And this is the standard representation used in speech recognition, which turns out to be not a very good representation for these nets. These nets are much better using a simpler representation, which is just the output of filter banks. This representation was designed to pre-process the speech that made it easier for a dumb machine learning method. But even if you use that, there's a standard database, which is regarded as rather old-fashioned by the speech community, but is very good for debugging new methods. It's called TIMIT, and it has about 3 hours of speech that's fairly clean and that's very accurately labeled. And the record on TIMIT, before we started doing this, was 24.4% errors at recognizing what the phones are. And that involved averaging many models. The students fairly quickly got down to 23% error using this deep net, which was a big advance. In speech recognition, that's quite a big difference. That's typically a few years of progress. And they discovered that it doesn't really matter how many layers you use. It worked best with 7, but 4's fine. And it doesn't really matter how wide you make the layers. You should make them at least 1,000 wide, but you can make them 2,000 or 3,000. And the main point of the research was, as long as you use plenty of layers and plenty of hidden units per layer, you'll get down around 23 to 24% errors, which is beating the records. Since then, it's gone down to 19.7%, with a couple of other tricks I'll tell you later. This has had a big effect on the speech recognition community. And now if you go to speech recognition conferences, they're all doing these kinds of, well, not all of them, a remarkably large number of these people who used to be fitting Gaussian mixture models are now fitting deep belief nets and getting better results. So for example, in the research labs at Microsoft Research and at Google and at IBM, they're all getting much better results using deep belief nets than they were getting using Gaussian mixture models. And they spent 20 years highly tuning these Gaussian mixture models. And they try these, and after one of my graduate students has been there for 3 months, they're getting much better results with these than with Gaussian mixture models. Okay. I want to show you some of the results from Yoshua Bengio's lab, showing what happens when you do the fine-tuning, because it's quite interesting. This is for MNIST, but with some extra variations to integrate more data. And these are the feature detectors it's learning in the first hidden layer. So what I'm showing you here is the weights from the feature detector to the pixels. So for example, this feature detector likes a stroke, a diagonal stroke like you find in a 2 or a 7. This likes the kind of thing you'd find in a 3. Those are the feature detectors that were learned unsupervised. When you now do fine-tuning, these are the feature detectors. And the point is you can't see the difference. Well, you can't see much difference. You think that one moved up, but that's just because I clipped off the bottom of this by accident. So really, these are the same. So the fine-tuning is doing hardly anything to the feature detectors in early layers. Nevertheless, it's making the recognition error go down a lot, because it's subtly adjusting the boundaries between classes. So if you don't do pre-training and you just train with backpropagation, this is the kind of performance you get. Notice 1.6 is about as good as you get, and most of the nets that they trained that way got about 1.8% error. If you do pre-training, this is with just one hidden layer. If you do pre-training, most of the nets are getting 1.4, but you do a bit better in some nets. And there's almost no overlap. If you now have 4 layers, there's really no overlap except when things went wrong. So there are a few cases when things go wrong. These nets do really badly. There's a long tail there. But basically, this distribution, notice it came down. The top end of the distribution came down and joined up with the bottom end here. And you got a distribution around 1.3, where these guys are fairly consistent and are doing pretty well. If you have 4 layers here and you use standard backpropagation on this data, you'll overfit, and so these nets are now doing worse. They've moved up a lot. So 4 layers is no good for standard backprop, and very good if you pre-train. Yeah?
So these are just started with different initialization?
These are just different random initializations, yes. So here's, with Samarabars, here's what you get if you don't pre-train. So 2 layers is slightly better than 1 hidden layer, and then it starts getting worse again. If you do pre-train, it keeps coming down to about 4 layers, and then it starts getting worse again. And this is considerably lower than any of those. So that's pretty convincing evidence that pre-training is a good idea when you don't have that much labeled data. This is a nice picture where what they did was they plotted out the functions being computed by the networks. So the point about these networks is you can't compare the weight vectors of 2 networks because they could permute their hidden units. So you could have 2 hidden units that are doing the same thing but the other way around, and now the weight vectors will look very different. And you could try and match up hidden units, but they're not going to match exactly. But you can estimate the function in the following way. You take a suite of test examples, you look at the outputs the net gives for those test examples. So look at the whole probability distribution it gives. So now you can see if 2 networks behave very similarly on all these test examples, and then you'll say they're computing a similar function. So you can take networks that are pre-trained and networks that are not pre-trained, and during the course of training, you can watch what happens to these networks in terms of the function they compute. And of course, these output vectors that they get for the suite of test cases will be high-dimensional things. There'll be 10 labels times the number of test cases, which I think were hundreds. So what you have to do is take those output vectors and reduce them to 2D. And you want to reduce them to 2D in such a way that very similar ones stay close. Most methods of reducing to 2D, like principal components analysis or multidimensional scaling, will emphasize getting the big distances right and the hell with the small distances. And that's not what you want at all. You want to get the small distances right and the hell with the big distances. There's a method called tsne that does that very nicely. You can find it on the web and all the codes on the web. It's the best method of showing data in 2D, this kind of data. And using tsne, if you don't do pre-training, your nets this is your initial random distribution of nets. So these are nets with random weights in. And this is showing that they all compute fairly similar functions. So that's where you start. Then you update the weights, and the colors change as you update the weights. And you can see the final bit of learning of this net here. And these are the nets that are not pre-trained. These are the nets that were pre-trained. So after the pre-training, you're here. And as you update the weights, you do this. And the point is, none of these are at all similar to any of these in the function they compute. These compute a bunch of different functions, which sort of fill this space. These all compute very different functions. And they're quite similar to one another and very different from these. So you're finding a different part of the space when you do the pre-training. And it's a better part of the space. It's better both in terms of the performance on the training data, but especially in terms of the performance on the test data. Okay. And to conclude this part of the talk about using backprop for fine-tuning after you've pre-trained, this is a kind of ideological slide. This slide is about what was wrong with machine learning for 20 years. Actually, call that 50 years. Machine learning went down what I think was a blind alley for a very long time, if you're interested in problems like speech and vision. Because it was trying to jump from the inputs to the answer. And that's a bit like, suppose you have a 5-year-old child and you'd like them to be able to do integrals. Okay, so you teach him to do integrals. Well, good luck. If you've got a 5-year-old child and you want them to do integrals, start off by teaching them to do basic arithmetic. That would be a better bet. And then teach them to do slightly more complicated arithmetic. And then teach them to do differentiation. And eventually teach them to do integrals. But going straight for the final thing you want is crazy. Now, the final thing we want may be discrimination. But we're much better off learning to do something else. So if you think how pairs of images and labels come about, or pieces of speech and the phone label for the piece of speech, here's 2 possible models of how you get an image and a label in graphical model kind of notation. One way is there's this underlying stuff going on in the world. This is a somewhat informal concept that I got from Rumsfeld. Stuff happens. Okay, so there's this stuff in the world that's happening. This could do with a little bit more mathematical formulation. That gives rise to images. Now, it could be that images then give rise to labels. And that would be the case, for example, if the label is the parity of the bits in the image, or the label is, does the top left-hand corner have the same color as the bottom right-hand corner? That would be a case when the stuff gave rise to the image and the image gave rise to the label. But that's not what you believe about most image label pairs. What you believe is that the stuff going on in the world, and the stuff going on in the world gave rise to the image, like there's a cow in a field, and the stuff going on in the world gave rise to the label. I mean, it may be your mother saw the cow in the field and that caused her to say cow. But the fact that it's a cow is to do with the stuff, not to do with the image. What's more, the image contains hugely more information about the stuff than the label does. So if you see a cow in a field, you can answer questions like, was it pointing to the right or to the left? Was it upside down or the right way up? Was it a brown cow or was it a black and white cow? Was it floating above the grass or was it standing on the grass? All sorts of questions you can answer. Were there other cows around? If I just give you the label cow, you can't answer any of those questions. So what's really going on when we get image label pairs is there's a very rich and complicated world, and that gave rise to an image. There's a very rich and complicated world, which gave rise to a label. This is a very low bandwidth pathway. There's only a few bits in a label. Log of the number of words you have. This is a very high bandwidth pathway. We know it's a high bandwidth pathway because we can look at an image and we can understand what caused it. In other words, we look at an image and we can get this stuff. And we're actually very good at it. I mean, I don't look out here and say, well, it might be an audience, it might be a forest, it might be a beetle. No, it's an audience and it's made of people. And we're very good at that. We very seldom get it completely wrong. So there's very high bandwidth between the stuff and an image, especially if you can move your head and you have two eyes and things. There's low bandwidth here. So if you want to get from here to here, this is just insane. This is a really stupid thing to do. You ought to take the image and figure out what caused it. And that'll be useful for all sorts of things. It'll be useful for naming what's there. It'll be useful for picking it up. It'll be useful for avoiding it. It'll be useful for getting an aesthetic experience. Once you figured out what's there, you can then associate a label with it. And this is a language learning problem. It's not a vision problem. And so if we could unpick the image to figure out what caused it, then associating labels would be easy. And it's just completely obvious that's what we ought to be doing. Of course, the reason I say it's completely obvious is because it's not, because most people think we ought to be doing this, and that's the obvious thing to do. But it seems to me it's completely obvious we ought to be doing that. Okay, so that's ideology. Now, I talked about doing generative modeling using stochastic binary units, and I kind of indicated that's a stupid idea because we're trying to invert computer vision, and computer vision is stuff full of real numbers, and we ought to be able to deal with real numbers somehow. So in particular, pixels have real valued intensities, and when we model writing, we can pretend it's sort of binary ink, and we can get away with these binary stochastic units. But that's only for modeling digit recognition. For real images, it doesn't work. And here's an interesting property of a real image. If you take a pixel, its intensity is almost exactly the average of its four neighbors, almost always. Now, occasionally it's very different. It's a very heavy-tailed distribution. But almost always that's true. And it's true very accurately. You can't model that using binary pixels. I mean, if it's an intermediate value, the best you can do is say the probability is 0.5. That doesn't capture the fact that the intensity is between 0.49 and 0.51 with very high probability. You can't capture that by saying the probability is 0.5. So we can't use binary units, even mean field ones. So what are we going to use? I'm going to take a somewhat circuitous route. Well, if we want to stick with integer values, we could use binomial units. That is, we could make 100 copies of our binary unit, all with the same weights, and we could ask how many of those copies get turned on. And that would be, we have our logistic probability, then the number that gets turned on is going to be n times p, and it's going to have some variance like this. And by making n big, then we can make, when we divide by n, we can get a small standard deviation. So by using binomial units, we can get things that are fairly sharp, and as we make n bigger, they get sharper. And that's the first thing we did to try and deal with real values. And that works moderately well. But there's a little twist on this that works much better. Notice there's no extra computation here. You compute this logistic of the total input that a unit gets once, so you get p, and then you just say the number of copies is a binomial whose expected value is np, and you can sample from that. But here's something that's much better to do. Compute that same p. Well, have logistic units. Have them all with the same weight vector, so they all get the same input, except that they have different biases. So there's a learned bias that they all share, and the first one here has the learned bias minus 0.5, and the second one has the learned bias minus 1.5, so it's got a higher threshold. This has the bias minus 2.5. You make the biases go up in steps of 1. And so if you draw the logistics as a function of x, they look like this. After you've been going for a bit, if you take a cross-section and you add up this plus this plus this, you get something that's almost exactly a constant. And what you discover is that a whole bunch of logistic units with offset biases like this behaves very like something else. So if you take this sum, as n goes from 1 to infinity, of the logistic of x plus 0.5 minus n, where n's the offset, for all different offsets, then that equals this. Now it doesn't actually equal it. This is in the exponential family and this isn't. But actually it equals it so well that if you plot the two in MATLAB, you can't see the one you plotted first because the other lines bang over the top of it. So you can take a logistic unit by sharing weights with other logistic units and by offsetting the biases, you can make it into a unit that behaves like this black curve here. You can make it fold down at the top by just making this sum not go to infinity, by making it go to big N or something, then it'll fold down at the top. And so you get something that's a sigmoid unit, but we're going to use it sort of in this range here. Also, you might note that this thing is now very similar to just a rectified linear unit. The only difference is in the little kink here, and that kink is to do with the fact it's got a soft transition from 0 to the sort of constant value here, constant slope here. So we can use units like this, or we can use just units like this green one, which are rectified linear units. Because it's very similar to a bunch of these logistic units, we can expect all our math to approximately go through. For the bunch of logistic units like this, all the math applies unchanged. So it applies unchanged to things that follow this black curve here, which is almost exactly this. And so you can just use it with that, and everything will work. Or you can use it with this green thing, and things still work. So in my lab, what we've been doing more and more is switching to these units. Yann LeCun discovered that, before we did, discovered that these units are very good for doing vision in his convolutional nets. Putting in rectified linear units makes things work better. And so my advice is take all your logistic units, throw them all away, you won't be sorry, and use a much simpler kind of unit, which is this. The output of the unit is the max of 0 and the input, except that you're going to add on some noise that's a function of this input. And I'll come to that in a later lecture, what the noise should be like. If you do it without noise, it works fine. Now you might be worried that when I backpropagate through this, the gradient is discontinuous here. It's got a perfectly well-defined gradient everywhere, but the gradient switches here. And you might think that will mess up your backpropagation. It doesn't. It just works fine. Because we're doing stochastic gradient. Oh, the other advice is do stochastic gradient descent. Of course, if you use a fancy method, like Hessian-free methods, or LBFGS and things like that, you have to worry about things like that. If you use stochastic gradient descent, it all comes out. Everything's so approximate anyway that you don't need to worry about more approximations. And it works just fine. So these units just work better. And anytime you see a benchmark for something, rip out the logistic units, stick in these units, fiddle around a bit to get the various learning rates and things right, and it'll probably work better. So here's, and you can do the learning. So if you, this is a case where I used those rectified linear units, which I call ReLUs, both for the data and for the hidden units. I trained a restricted Boltzmann machine in exactly the same way, except I'm using rectified linear units here. And just assuming that this math will still work, even though there's no real justification for it other than one I just gave you. And it works just fine. It's important to add sampling noise here, so add some kind of noise, otherwise it overfits. And it learns good density models of images. So here's a database that Jan LeCun developed, called the NORB database. It has animals, humans, planes, trucks, and cars. The humans these are American toys. So they're little plastic toys. He painted them all green, so you can't use color to discriminate. Then put them on a turntable and got lots of viewpoints of them in different illuminations. And what's interesting about this data set is the test items are different objects. So just being very good at dealing with the geometry of the training things isn't going to help. You have to be able to generalize across classes and generalize from just a few specific examples seen in multiple viewpoints. Because these are American humans, they're all carrying weapons. Okay. In Canada, it's quite different. There's lots of lighting conditions, lots of viewpoints. Not that many training cases, considering they're quite complex images. They're stereo pairs, by the way, and the same number of test cases. There's various versions of this data set, and we're using the version with a sort of vanilla background. If you look at the distribution of intensities here, what you see is the intensities look like that. And so I'm going to measure intensities downwards. This is the bright background. I'm going to set that to 0, and then I can use rectified linear units by measuring intensities this way. So more active means darker. And I'm going to simplify the images in other ways by cutting off all the edges. The edges are all there because Jan likes to use convolutional nets. And so he likes to, all Jan's data has big blank edges around the edge to make it easier to use convolutional nets. So you can throw those away. And I also downsampled it in the crudest possible way by just averaging 4 pixels. And I also threw away one of the stereo images. So I've simplified the data a lot, and then applied rectified linear units, like that. If you use the full data and do logistic regression on the raw pixels, you get that kind of error rate. Support vector machines, trained by someone who knows what they're doing, gets that error rate. And Jan's convolutional nets get this error rate. I should say that now people are down to about 2% error on this data. If you do my reduced data, which is 132 by 32 image, and you do logistic regression, you can see you get worse. You've got less information now, and you're about 1.5 times the error. If you now learn layers of ReLUs, if you use a couple of layers of rectified linear units and apply logistic regression to those, you do better than support vector machines. So that's saying these rectified linear units, and you do quite a lot better than you do if you use logistic units. If you use logistic units, this would probably be sort of 12 or 13%. There's a paper a couple of years ago that has better results than this, but basically, so this was from the early work on the paper, basically rectified linear units applied to images work nicely, and then take higher layers of these, apply logistic regression, and you get pretty good classification. You also get interesting features. These don't show up very well, but I think you can see here you've got quite long edges, which are different from the normal features like here. There's a long edge. They're different from the normal features. I should show one at the top where other people can see it. Here there's a long edge. Here there's a fairly global feature. It's got a piece here and a piece here. They're different from what you get if you use logistic units. And if you look at what these feature detectors are doing when you show it an image, with a logistic unit, if you think of it as stochastic, which is how we pre-train it, it can either say nothing or it can say ping. With these units, most of them say nothing most of the time. And a few of them go sort of ping, ping. And ones like this one, when they see what they like, they go ping, 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 ping. That is, they have an activity of like 10 or 20. And so they're sort of far more discriminating. And it turns out that's just a much better thing to do with these hidden units. It makes everything work better. It allows a unit not to saturate so fast. So when it sees something it likes, it can tell you it likes that. But when it sees something it really, really likes, it can tell you it really, really likes it. And a logistic unit can't do that. So having said all that, I'm going to now go back to the standard way in which most people model pixel intensities in these deep nets, or model real-valued inputs. And it's what people are still using for speech, and they shouldn't be. We're going to write down an energy function, but it's going to be an energy function where we have Gaussian visible units and binary hidden units. And so the first thing we do is we take our visible units and we put a quadratic energy function around them with a bias. So we say if a visible unit departs from this value, that costs. And this quadratic containment eventually will always contain any linear function like this, as long as the slope isn't infinitely steep. So this is going to stop things blowing up and going off to infinity, which is going to mess up all our probability distributions. That's this term here. And notice there's a plus there. The energy is plus how much the visible unit departs from this mean that it's meant to have, normalized by some variance. Then we have the terms that involve the hidden units. There's the normal bias term for the hidden units that says if you turn on a hidden unit that has a big positive bias, you win, you get low energy. And then there's the interaction between the binary hidden units and the Gaussian visible units. And that interaction term has to be scaled by the standard deviation of this Gaussian containment term. Because those are the natural units to measure a Gaussian variable in. Those are what are called z-scores. They're just the sort of natural units. And they're the ones that need to be combined with these Bernoulli variables. So that's the energy function for a restricted Boltzmann machine that has Gaussian visibles and Bernoulli or binary hiddens. Now, when you try learning models like this, it doesn't work very well. Everybody tries it. Everybody discovers it doesn't work. And everybody then uses a cheap hack, which is good enough for learning features, but is very unsatisfactory. So here's the problem. Here's a Gaussian visible unit, and here's a binary hidden unit. Now, the effect that the visible activity has on the hidden unit has to be scaled by the standard deviation, has to be divided by the standard deviation. And that's equivalent to saying the effective weight here gets divided by the standard deviation. So you take this visible activity and you multiply it by this. So the effective weight here becomes very big when this standard deviation is small. In other words, if you measure the pixels with a very small standard deviation for the residual noise, then if you get a big pixel value, that's extremely significant and should have a big effect on the hidden units. And that's what this is saying. Now, when you look at the effect of the hidden units on the visible units, you get the same scaling, but you also get a factor of sigma squared that sort of dominates. And so, in effect, you're scaling the weights in this direction by sigma times W. And so that says when sigma is very small, the binary units have a very small effect on the visible units, because you get very small standard deviations here, so a little bit of top-down input hardly has any effect. And so as you learn sigma, it's equivalent to making these weights going up much bigger, if you make sigma small, and these weights coming down much smaller. And so you get to a situation where you don't have nearly enough effect of the hiddens on the visibles to reproduce the data, and you have much too much effect of the visibles on the hiddens, so they all saturate. They're all driven firmly on or off, depending on whether the sum of the input is positive or negative. And so whenever you try to learn, whenever you try to learn this variance, it doesn't work. Just occasionally it works if you happen to have many more hiddens than visibles, and it happens to be, suppose you have 10 times as many hiddens as visibles, and it happens to be that the right value for this is 1/10, then it will often work out. But if the right value for this is 100th, it won't work. So what you really want to do is somehow get the effect of getting many more hiddens when you have to have a small standard deviation here. And there's a very simple way to do that, which makes these things work much better. So what we want is, when this gets smaller and these weights get bigger, what we'd like is to have many, many more hidden units, so that this can turn on lots of hidden units, and the hidden units, even though the weights are quite small, so you can keep these weights very small, that gets divided by a small number, you get soft input to these hidden units, you turn on lots of them because you have lots of copies of this guy, and that now provides lots of top-down input here, which is enough to drive these visible units, even though they have very high precision. And so the way to do that is have lots of copies of this, make the copies have offset thresholds. In other words, make these be like those rectified linear units. And if you do it with binary units, and you want to get the math right, what you do is you have logistic units with offset biases. And so imagine a whole column of logistic units here, whereas you've got the column the biases get higher, biases get lower, the thresholds get higher. And so now, when I make sigma, if I make sigma be half as big, I make the residual noise be tighter, then twice as many of these guys will turn on. And therefore I'll get much more top-down input, which is what I need. And now everything works fine. So all the problems that came from trying to learn these residual variances were because you didn't do that. And I'll tell you what most people do, which we did for years, which is you say, OK, when I try and learn this, it all goes wrong. So I'll set this to be 1, and then I won't try and learn it. And that's a completely ridiculous thing to do. Because what you're saying is, I have a model, it has residual noise in it, and I'm going to take my data, you also have to normalize the data. I'm going to take my data and normalize my data to have unit variance. And then I'm going to say the variance of the residual noise is unit variance, which is equivalent to saying noise explains the data. I can't explain the data any better than the residual noise level. That's what you get if your model explains 0% of the variance. And that's what people run, and that works remarkably well for finding features, but it's very unsatisfactory intellectually. It's clearly the wrong thing to do. And the reason that you had to do that was because you're using binary hidden units. As soon as you switch to these gangs of binary units with offset biases, which is equivalent to a rectified linear unit, almost, then everything works out fine and you can learn these variances. Okay. So if a subsequent speaker says you can't learn those variances, you can explain to them that you can. So these rectified linear units have a nice property which I call intensity equivariance. Let's suppose we give them a 0 bias to make life simple. Now, if I take the image and I multiply it by A, then my representation of the image, which is the activation of these hidden units, I'll have A times as much activation there. Because you see, if things are below threshold, they'll be 0. And when I multiply by A, since they've got 0 biases, they'll stay below threshold, so they'll stay at 0. And if they're above threshold, they'll just be linear. So it's a very nice property to have this flat and then linear. It's not linear, it's highly nonlinear because of this rectification. But that doesn't stop it having this property of linear systems. So as you know, linear systems have two properties. They have this property, and they have the property that r of x plus y is r of x plus r of y. They don't have that at all. They've completely given up on that property. But they do have this property. And this makes them equivariant to intensity. What that means is, if you make your rectified linear units have zero biases, and you have multiple hidden layers of these guys, if you put in an image that's 3 times as bright, everything will be 3 times all the way through. It'll just pass that straight through without changing anything. All the nonlinearity is about the direction of the intensity vector. It's not about its length. Okay. Convolutional nets have a little bit of this kind of invariance, which is the representation of a shifted thing is the shift of the representation of the thing. So if you have a convolutional kernel, shift things over, it's not that the representation is invariant, the representation is equivariant. The representation shifts over. You then try and get some invariance by pooling with max pooling or something. But the basic convolutional thing gives you equivariance, not invariance. I'll give a whole lecture later on Thursday about why equivariance is what we should be going for rather than invariance. This is just an example from some time ago of Alex Krzyzewski using Gaussian ReLU RBMs to learn nice features. These were the features learned on color images before fine-tuning. And then when he discriminatively fine-tunes, they get cleaner. So you'll notice there's a difference here. And these are pretty nice features to have on color images. You have low spatial frequency color contrasts, and higher spatial frequency intensity contrasts. And each of these receptive fields is actually, for each weight in there, there's a weight to the R channel, a weight to the G channel, and a weight to the B channel, the RGB. And so the fact that they're black and white says they made those weights exactly equal. So it's learned to ignore color. And so most of the filters pretty much ignore color, especially the high frequency ones. And then you have low frequency filters that attend to color. That's a very interesting property I may talk about later. And it's because of the way the world is. Your brain does the same thing, and people thought your brain did it because of evolution or something. Well, it may do it because of evolution, but evolution did it because of the way the world is. Many of the edges in the world have no color contrast, but occluding edges almost always have a color contrast. And this net really picks up on that. Yeah?
You showed an example earlier where the fine-tuning didn't have any much effect.
Yes.
Here
It has much more effect, yes.
So is that due to the
What's happening here is this is much more complicated data, and it's a much harder discrimination. And so the fine-tuning has much more work to do. The pre-training produces reasonable features, but because it's more complicated data, the fine-tuning has to do more. It can't just change things a little bit and get the answers right. Also, yeah, I'll leave it at that. Oh, I'm running out of time. That's okay, though. So the sort of lesson of the second half of this lecture is that rectified linear units are what you ought to be using for most things. That nonlinearity is, models need to be able to sweep things under the rug. They need some way of ignoring variation, as well as some way of attending to variation. And that nonlinearity allows you to take ways in which images change and ignore them. Because if you're below your threshold, then you're completely insensitive to changes in the image until you get above your threshold. And that's an important property to have. It's not just you want to be able to attend to changes, you want to be able to ignore, most changes you want to ignore if you're trying to do classification. And so ReLUs are good for that. You can think of the linear part of the ReLU as much better than a stochastic binary unit at modeling covariance in the image. So as you know, something like principal components analysis picks up on the directions of high covariance, and it models the covariance structure of the image. Well, when you're above threshold, these things are just linear. So they'll act just like principal components in grabbing directions of high variance. I mean, they won't necessarily get the directions of highest variance, but they'll be able to model the covariance of pixels very nicely. So you've got this ability to sweep things under the rug when you're below threshold. Above threshold, you can model covariance nicely. Whereas if you take binary units, the only way they can model covariance is by having a whole bunch of binary units with different thresholds, which turns back into a ReLU. So if you have a whole bunch of binary units with different thresholds, yeah, let me see if I can say that better. If I have two pixels, I and j, and they have the same intensity, okay? And I want to model the fact the intensity is the same without knowing what it is. I want to model the sameness of it. I want to get at that covariance structure. The way I would do that with a binary unit is by saying, okay, I get all excited when I see a 0.1 and a 0.1. And then I have to have another binary unit that says, okay, I get all excited when I see a 0.2 and a 0.2. And if you have enough of those guys, then you can model the fact that the things are correlated. But you have lots of parameters. But if you use this trick of sort of tying parameters together, so you use the same parameters, but change the threshold, then you get a rectified linear unit. And you can think of that as a whole gang of binary units that's been made efficient at modeling covariance structure by sharing all these weights. So for different overall values of I and j, it can model the fact that I is always the same as j by having equal weights to I and j. Okay. So rectified linear units capture covariance structure, but unlike PCA, they capture different covariance structure in different images because the rectification determines whether the thing's in its sort of operating range. So sometimes, because it's below its threshold, it won't be modeling the covariance at all. It doesn't care about covariance below its threshold. It only cares above its threshold. So you can think of it as something that models covariance structure, but can be turned on and off. So in some images, it can model certain covariance structure, in other images not. That's very useful for capturing things like edges. So if you ask, what is an edge? Well, there's an obvious definition of an edge in an image, which is it's something that's bright on one side and dark on the other side. It turns out that's not a very good definition. For a start, it might have been bright on the other side and dark on the first side. But actually, if I take an edge that's bright here, it's a vertical edge, right? It's bright here and dark there, and dark here and bright here, you'll just see a single edge, even though there's a region where the intensity is equal on two sides. So bright on one side, dark on the other side is not a good definition of an edge. Here's another reason why it's not a good definition. If you have stereo, you can see an edge just because of the difference in stereo depth of random dot patterns, where there's no intensity change. Then you've got texture edges. You've got all sorts of edges. And initially, you think you're going to need a long catalogue of edge detectors. Turns out you don't. There's a very simple definition of an edge, which is an edge is this. If there's a vertical edge, it's a very bad idea to predict this pixel from the pixels over here. However you're doing the prediction, you shouldn't predict across the edge. So a vertical edge is a breakdown of the covariance structure. It says you've got a nice covariance structure over here, you've got a nice covariance structure over here, but across this edge, the normal covariance structure is broken down. The covariance structure you find in smooth textures or smooth stereo depth is broken down. And what that's saying is the things that we find most important in images, like edges, are not really to do with intensities, simple intensities. They're to do with changes in covariance structure. And so capturing covariance structure is really important. But the covariance structure varies. And these ReLUs are very good at doing that. Marco Aurelio Ranzato, towards the end of the talk, will probably talk much more about capturing covariance structure in images. But for now, let me just talk about one other way of capturing covariance structure, which actually is quite like using rectified linear units. And we thought for a time that rectified linear units would be much better than this other method. So there's a method called factor analysis, which is basically principal components done right by a statistician. So in factor analysis, you have a Gaussian prior over your factors, and then the factors give rise to the pixels in this case via a linear model, and you have residual noise models for each pixel independently, which might be different for each pixel. So it's just a linear model where there's Gaussian underlying latent variables that are meant to explain the data, and there's less of those Gaussian variables than there are of the pixels in factor analysis. That's quite a good linear model of lots of things. For images, if you want to make it a really good linear model, what you do is use mixtures of factor analysis. So you say, if you give me a patch of an image, it might have a vertical edge in which case it's got very different covariance structure from something without a vertical edge. So I need a different factor analysis model that knows not to model covariance across the edge. So to model a set of image patches, the best model people know, a much better model than any of the other models, is a mixture of factor analyzers. That's a big surprise. It works better than all the fancy models people doing computer vision came up with. Yae Weiss showed this a couple of years ago. You get much better density of the image by using a mixture of factor analyzers. We've made it slightly better by a slight modification, but basically that's the best model there is of image patches. And what a mixture of factor analyzers does is says, I'll use different covariance structure for different images, but I'll use a linear model that grabs covariance structure. Now what these rectified linear units are doing is they're saying, for each image, I'll turn on a subset of them. But unlike a mixture factor analyzer where you have non-overlapping subsets, so in a mixture factor analyzer you can use these factors, or these factors, or these factors, but you have to decide which subset you're going to use. Whereas with rectified linear units, the image decides which ones are above threshold, and then you're using all those. So there's a subset you're using, namely the ones above threshold, but it's much more of a mix and match than a mixture factor analyzers. You can use any of them together if they get to be above threshold. And we thought that would make a better model of images, and it turns out it doesn't. Mixture factor analyzers is still king for modeling image patches. Somehow I would like these rectified linear units to beat mixture factor analyzers, but the sad fact is they don't. I think I'll finish on that sad note. Okay.